Hi, everyone. I'm Milinda Perera. I'm a software engineer in the anonymization team at Google.
And I am Miguel, and I am a product manager at the anonymization team at Google. And today we'll talk to you about the ways in which we are improving usability of differential privacy at scale. First, let me introduce you to the problem. Why is there a usability problem in differential privacy? Let's just start with a hypothetical use case. Imagine that we have a dataset that has private movie ratings. That dataset is keyed by this pseudonymous ID. It has timestamps at a daily granularity, and it has movie ratings that go from 1 to 5, where 5 is the top rating. It also has the name of the movies that were rated. Now, imagine that we can perform just a simple aggregation. For instance, we just want to count the number of movies that have a specific rating on a specific date using the group by operation and the count aggregation method. This looks private at first, but if you look closely, some counts might be 1, which is a single user at one day. You can use this information and compare it to other databases, such as externally available public rating datasets. And if there is a user rating for the same movie on the same date, these can be used to de-identify users. So there's a pertinent question. How can we anonymize this data? Well, imagine that you had a SQL engine that is able to do differential privacy. And if you're interested in learning more about SQL engines with differential privacy, you can check out the paper that's linked on the PDF. So let's say that we do we change the query to look like this. One of the problems that comes up with differential privacy is that they require parameters such as epsilon, delta, and clamping. So how can people choose these values? What's the principal way of choosing them? Well, this depends on the utility and the privacy that we want to guarantee and might be different from case to case. So this is where the usability problem comes. People just want to anonymize their datasets and want a simple way of doing it. So that's why we came up with a way of quantifying privacy and utility. What we will present to you today tries to bridge the gap between that usability gap of differential privacy. As you're probably aware, there are many papers describing many methods to perform differential privacy, but the space of making it more usable has been vastly overlooked. The way that we did it, and we'll explain it to you, was by defining privacy versus utility metrics. We also provided infrastructure so that people could safely and efficiently compute them at scale. Think of computing metrics on terabytes of data. Finally, we allow for a self-service model so that users can see in real time the impact of privacy parameters on their data, and if they want to, they can tune them in real time. Now, to give you more information, I'll pass it over to Milinda.
Hi, everyone. So now I will give you a demo of our system, and I will also explain how the system addresses the usability concern of differential privacy. So this is how our system looks like. First, I will explain to you the different components in the system in the UI. And then I will explain how it helps with the usability concerns with differential privacy. And finally, I will explain to you how one would use this tool to tune parameters to anonymize with differential privacy with the example that Miguel mentioned earlier. So in our tool, we have different sections for different parameters and controls. So on the left, you can see the typical parameters one would have to specify if they were to anonymize using differential privacy. So at the top, you have anonymization parameters, epsilon and delta. As you know, these parameters control how anonymized the output is. And next, you can select different infrastructure configurations. So these are the infrastructure, like the general infrastructure we have at Google. So Flume is this MapReduce style infrastructure. SQL is SQL-based engines. And you can also select custom and then set specific specialized parameters like noise distribution type, Laplace or Gaussian distribution, etc., etc. So for this demo, I will stick to SQL. So it's compatible with the example Miguel showed earlier. Next section is about data utility parameters, also known as sensitivity parameters. So these parameters control how much effect any given user can have in the data, right? So the more effect a user has, the more noise we have to add to hide that much change in the data, right? The last set of parameters here are called filters. So these are not differential privacy parameters. So they allow you to look at certain areas of your data and then see what happens to, say, in values in a particular range. So you can dive into like detailed analysis. And then on the right side, you can see at the top some metadata about a particular data set being analyzed. So here we are analyzing this data set with movie ratings. So what we call partition here is how we are grouping the output by. So here it's the date and the rating a particular user has given for that date. And then the next field here is called the partition value, essentially what type of aggregation we are doing. We are counting users. And then in the next section, you can see anonymization statistics, right? So here there are different types of statistics. At the top, you can see something what we call the threshold. So these are very important intermediate parameter in anonymization. So the idea is if say in this case, a particular date and rating combination, if there aren't enough users, say if the number of users in that particular bucket is less than that number, we won't be releasing that because it's too sensitive, right? It doesn't allow us to release that and then claim these privacy guarantees required by epsilon and delta, chosen epsilon and delta. And noise standard deviation is quantifies how much noise we are adding to the movie counts in this case. And then there are a couple of other parameters here as well. So these basically talk about how many partitions you have in the underlying data. So there are about 10,000 combinations of date rating pairs. And here you can see how many partitions are there in the output, right? You can see there is some loss, but it's almost 100%, 98.9. And then here, another important parameter. So this is again, the intention of these two parameters is to give you like a very high level idea of accuracy loss, right? But we should keep in mind there's so much you can explain by just one number, right? So this parameter is basically saying if you add up all the movie counts across all the partitions in the row output, what's that value? And here it's the same thing computed over anonymized output. As you can see, there's a 70% change, right? Like there's a 70% drop. So it gives you some kind of a very high level idea of accuracy loss. Again, it's not the only thing to look at. And we also have several plots that dive into these like the changes introduced by anonymization. So this plot is a histogram where we show the distribution of values in the anonymized output and the row output. So the x-axis shows different value ranges, like in this case, movie count value ranges. And the y-axis is the number of partitions with values in that range. So if I selected this one, you can see there are the value range is 60,000 to 65,000 movie counts, and there are 50 partitions with values in that range in the row input, and in the output there's only one partition. There's a big change. As you can see, there's actually quite a big change. Now, another thing to point out here is this graph is shown in the log scale. But in reality, it's more like that. It's more like long tail distribution. But looking at the log scale helps you emphasize the difference. It's good for like detailed analysis. The next plot is about how much change is introduced by the anonymization pipeline, right? So here at the in the previous plot, you can see the overall difference. This particular plot dives like tries to explain how how this change is distributed. Again, it's a histogram. X-axis is the relative change, right? Like buckets of relative changes. And the y-axis is the number of partitions that experience that amount of change. As you can see with the given parameters, most of the partitions have changed between 40% and 90%. It's actually quite bad accuracy-wise. The last plot is about the partitions that you don't get to release at all because of anonymization. At the beginning, I mentioned there is this parameter called thresholding, right? So if you don't have enough users above this threshold, you don't release that partition at all. So this plot, again, another histogram, shows you how those partitions are distributed. In some cases, you might want to look at, okay, what can't you release? So you can address that in other ways. Now, how does this help with usability? Now, if you look at the left side, you can see these parameters, epsilon, delta, right? Data utility parameters. When you look at that, like, what does it mean? Does it give you an idea of how much data loss you'll have to suffer, and how much noise are we adding? Like at which point don't we release things, right? Privacy parameters. It doesn't give you any of those, right? So the goal of this tool is you can like set these parameters and get those anonymization statistics in pretty much real time. It takes seconds to compute this. You don't have to run lengthy, like long pipelines to compute these things. You can click a button, get the values, and make the changes. Again, see the change, essentially tune the parameters. So now I will walk you through an example where I try to get the most utility out for my use case, right? For example. So again, in this particular use case, I'm analyzing the movie rating dataset. So you have the date rating partitions and the movie counts. And say I start with these parameters. So when I click compute, I see in the output, I get to keep almost all the partitions, but there's massive data loss, massive accuracy loss. So what do? So the first thing I would do is say for my use case, I'm only interested in partitions with at least 100 as the movie count, the aggregate, right? So I can set that value here. I click compute, and you will see nothing changed. I mean, it's pretty much the same, right? I get to keep more partitions, right? Because I don't care about these low count partitions, but the accuracy loss is still bad. And if you look at the two distributions, they are pretty much identical from the previous one. Now, the next step I would do is I would say, let me increase the sensitivity bound, the contribution, maximum contribution I allow for a particular user. Say I set it to 10. Again, I try that value, and you will see now the accuracy actually went to 70%. So 30% drop there. I still get to keep almost all the partitions, which is great. But because I increased the sensitivity, the noise standard deviation increased. Now it went from 2.8 to 28. It multiplied by 10, essentially. If you look at the two distributions, now they look better, right? So at 60, earlier, I was able to keep only one anonymized partition. Now I get to keep 4. This is again the log scale, right? But it's getting there. Right? It's not quite as accurate as I like. If you look at the change distribution, before it was like between 40% and 90%, the change. Now it's, I would say, between 5% and 50%. So less change. Again, could be better. So as for the next step, I would try 100 for the max contribution limit. And if I click compute, you will notice again, I get to keep almost all the partitions, and the partition value is actually quite accurate as well, right? It's like almost 100%. And if you look at the two distributions, they also very nicely overlap, right? Which is nice. And if you look at the distribution of the change, now almost all the partitions are less than like 10% change. A majority of, I would say, like around 5% change. Say, like for my use case, I like these numbers. I like the accuracy loss. It's something I can tolerate. And the distribution is also quite similar to the actual data distribution. And I might decide, well, these are the parameters I want to use. I would just set these parameters in my pipeline and run the pipeline once and for all to anonymize. So this way, the benefit to me as a product team is I don't have to do this analysis manually, come up with these plots and metrics manually, and I don't have to run the pipeline many times. So with this tool, I can just experiment with the different numbers, find the number that works for my use case, and anonymize once. Now, one thing I want to notice here is, again, the numbers, the actual utility parameters you pick, again, depends on the use case, like Miguel said earlier, right? So in this particular case, I'm assuming I can work with only values at least 100, and these are the parameters that work for that those requirements, right? And another important thing I want to point out, now we changed all these parameters to get to the parameters that we like, the combination of parameters we like, without touching the epsilon and delta, which is very important, right? So we didn't relax the privacy protections, but we still got a lot of utility out of the data. Now, with that, I will quickly explain how our system architecture works. All right, let's go. Okay, so this is the overall architecture of our system. So we divide how we generate this analysis into two phases. We have the phase where we create the analysis, and we have the phase where we weave the analysis. We try to distribute the work in these stages in various parts, because applying differential privacy can be really costly, right? So we have this intermediate data format called sketches, what we call a sketch. So the idea is this is a intermediate data format that allows us to apply differential privacy in real time very efficiently. But it also takes less space than the underlying source data. So that's something we create during the create analysis phase. And when you render the analysis, we primarily rely on these sketches to compute these metrics in pretty much real time. All right, and as a couple of highlights of our system, as you can see, you can actually run this analysis and get the output within seconds. Our median query latency is around 10 seconds. And the time it takes to start with the raw data set, create the sketch, and view the analysis, the entire end-to-end process takes in the order of minutes, maybe 15 minutes in most cases. And we found out through our internal studies and experiments, product teams do find this analysis quite intuitive and useful, and they are able to find the right differential privacy parameters through this analysis, and that's what our goal is, right? To make differential privacy more useful. As for future work, we are planning a couple of directions. So the very first one is to open source this work. So not only people within Google, but also outside Google can use this analysis and use differential privacy more. And also, we think once by open sourcing this, we can get the community to build upon what we have, right? Make it even better, right? So we are considering open sourcing these tools as part of our open source offering. The second thing we're exploring is introducing local differential privacy into this tool. So local differential privacy is a model where we apply differential privacy at the point of data collection, as opposed to you collect raw data first and then apply differential privacy on the server side. And the third direction we are exploring is to introduce more functions into the tool. Right now, our tool support count and sum operations, but there are other functions we should support. All right, with that, I would like to thank you on behalf of Miguel and I and Google for attending this talk. Thank you so much.